Okay, we ended the last lecture with kinetic energy and a nice example of kinetic energy and the relationship between work and kinetic energy and potential energy. They're just going to talk about that here. So when energy can do work against various things. These are just some examples. In mechanics, work against inertia, that is, if something's at rest, for example, and you want to get it moving, or if something's moving at a constant speed and you want to change that speed, that's work against inertia. Work against gravity, like lifting a book in a bookshelf from one shelf to another. If you lift it up, you're doing positive work because the book is gaining potential energy, and then if you lower the book to a lower shelf, you're doing negative work because you're taking energy away from the book, potential energy. Work against friction, if you just push an object across a table, for example, push a book across a table, you're doing work against friction because there's friction between the book and the surface of the book and the surface of the table. Work against shape, for example, if you take a piece of metal and you bend it, that is what we call work against shape. And then work against any combination of these, and there are other ones too. So alright, so here's just some pictures. Work against inertia. You have a car, you have to push it. Working against gravity, so you're lifting something up from the floor, let's say. Work against friction, pushing a refrigerator or something across a level floor. Squeezing a spring, for example, or stretching a spring. So there's many forms of energy. This is just some of them. Mechanical energy, which is the kinetic energy plus potential energy. There's electrical energy, there's also magnetic energy, there's chemical energy, there's energy in radiation, in electromagnetic radiation, which is part of the entire spectrum, which visible light is part of that. There's nuclear energy as well. There's also heat is a form of energy, sound is a form of energy, so there's all of those as well. So energy form conversion. So we're getting towards what's called the conservation of energy. So any form of energy can be converted into any other form of energy. Energy flow from one form to another is a natural process. For example, let's take a look at the bowler. Right, the bowler does work against the bowling ball by giving it kinetic energy. The ball rolls down the lane. It actually has rotational kinetic energy as it does so. We didn't really talk about that, but that's another form of energy. And then it'll do work against the pins by giving them some kinetic energy. If you're lucky enough to hit the pins. All right. So this is a great example. Is the pendulum. So you always have to have this reference point. And so the logical point would be the pendulum just hanging from the ceiling or something like that, where the bottom of the pendulum is the reference point. So that would be, for example, zero potential energy, as it indicates here. Now, if you were to do work on the pendulum by just lifting it through some height h, and then so what you've done is you've given it you've given it potential energy. And then when you let it go, what's happening is the moment you let it go, all the energy is still in the form of potential energy. And then as it begins to move and swing downward, some of that potential energy is going to turn into kinetic energy. But as it does so, this number, the total potential energy and the total kinetic energy, will remain constant. And so down here, halfway through the swing, half the energy is in the form of potential energy, half the energy is in the form of kinetic energy. At the bottom, all this energy that was up here is now in the form of kinetic energy. So we'll do some examples with this, and you'll see. So this is really the statement for mechanical energy anyway. This is the statement of the conservation of energy in equation form, is the total energy is fixed, it's constant. And I'll show you that in a little bit better, more useful manner, but it's a fixed quantity. The total kinetic energy plus, the kinetic energy plus the potential energy, even although they may vary individually, their total remains fixed. All right, so that's the idea of the conservation of energy, and as far as mechanics goes. Okay, so let's get with the full version of it. So energy is never created or destroyed. Energy can be converted from one form to another, but the total energy remains constant. And we'll do an example using free fall in just a moment. So they kind of set it up right here. Is for example, if you have an object and you drop it, the potential energy lost will be equal to the kinetic energy gained. And so the potential energy is mgh, right? Mass times gravity times the height, and the kinetic energy is 1/2 mv squared. And so, for example, you could use this to solve for the final velocity. If you drop something and it was just about to hit the ground, this equation right here describes the final velocity. Okay, so like I said, I'll do an example of that. They're showing you that here. They actually put some numbers in. I'd rather just do my own example with that. This is just showing us, how energy is used. Primarily we use petroleum and coal, or these two together are called fossil fuels. I'm sorry, there's natural gas as well. So you can see the vast majority of energy that we use as humans is in the form of fossil fuels, and not as much certainly in the form of nuclear or renewable energy. This is just a tiny sliver. In fact, the reason I'm bringing this up is that's what your first essay is about. Is why is it that we're using so much fossil fuel currently, even though gas prices are not so bad right now? Years from now, there's just so much fossil fuel in the ground, and eventually, we're going to use up all that's there. And the price of these fossil fuels will go up and up and up. And so eventually there's going to come a point where we're going to rely more and more on wind power and solar power, even hydroelectric power. So that's why I have you write an essay about that. All right. I'm going to skip over this. Okay, so they're just showing you some different. So what I want you to do in the essay is pick one of these forms of renewable energy, energy that you can keep. Well, this is not renewable. Fusion, nuclear is not a renewable thing, but renewable. Let's define that right now, just for the sake of argument. Basically, if you take a tank of gas and you burn the gas, you burn a gallon of gas. Not necessarily the whole tank, but just a gallon of gas. You don't ever recover that. You don't get that back to use again as a form of fuel. These, except for fusion, are renewable, so you can keep going back to them. The wind is another example of that. All right, so there's some more information if you want to write about one of those things. All right, so that's basically the end of chapter 3. Let me do some examples now. All right, so here's my example. I just have an object. It could be a ball. It doesn't really matter, and it's falling through a height h. Oops. Well, sorry, I meant to write h. All right, so it's falling through a height h, where this is the height h, and let's say we measured h to be, I don't know. We'll give it value. So let's say h is 9 meters. Okay, so it's going to fall through a height of 9 meters, And what we want to know is what this final velocity is. So what is the final velocity? And the other thing about these problems, and this is true for Chapter 2 problems as well, is the velocity at the top. In this case, since it's falling downward, the object is falling this way, the velocity at the top is going to be 0. Right? And this would work just as well if the object were going up, right? At the highest point, the velocity at the top would be 0. So we're actually going to get away from this initial velocity, and we'll say this is the velocity at the top. So I'll use t for top, and this velocity final. We could also call, just for the sake of argument, the velocity. And the reason I'm doing it this way is some of the problems in your book ask you this, is the same as the velocity at the bottom. So we want to know what's the velocity at the bottom. And what we have to work with is the conservation of energy, right? So the basic idea here is the sum of the energy at the top will equal the energy at the bottom. So I'll use top and T for top and B for bottom. All right, so again, we have to set up, when you have these things where an object is falling, we have to use some kind of reference frame. And so since we have this height of 9 meters, it's 9 meters above the ground right here. So at that point, or that reference frame,